We come now to the next presentation that will be given by Jutta Trube, who is the Director of Photovoltaic Equipment at Germany's VDMA, which is, with over 3,000 members, Europe's largest networking association for mechanical engineering companies. Jutta has worked for over 5 years with VDMA in that position, and in her career she has been working for several companies in the semiconductor solar sector, and was responsible for R&D development, among others, that applied films and live-volt optic. So we're very, very happy to have Jutta now present us the latest on solar modules from the recently released ITR PV roadmap, which is always a pleasure and great piece of work to read. Jutta, the floor is yours.
Thank you, Michael. I will try to get my screen shared. Okay, so can you see my presentation?
Yes, it looks good.
Okay. Thank you. So thank you very much again. So I will present our results from the 12th edition of the ITR PV. And Michael, you just said that I'm from VDMA. VDMA is the largest federation of European engineering, and I'm in the sector of photovoltaic equipment. And my members are all manufacturers or suppliers for the entire process chain of photovoltaic production for crystalline as well as for thin film photovoltaics. And we run now since 2015 the ITR PV. I will give some general outlook on the statics and the status on the PV learning curve. Then I will present some results from the 12th edition, starting from the crystallization wafer through cell module and to the smart fab status, and coming out with an outlook and a summary. Now let me start with some generals on ITR PV. Say we have, as I said, this year the 12th edition, and this year we have had 65 contributors all over the world, and we cover from silicon through the system the complete value chain. Typically we have, say, the data gathered from our participating companies. We at the VDMA then processing these data, and together with our international chair group, then we discuss the results and decide which diagrams should be in the ITR PV, and this will then be in the edition. So the edition can be downloaded freely on our webpage. I will have an internet link later on. This year we have slightly less figures because, which I will show later on, the microcrystalline silicon gets nearly out of the market, so we removed some of the diagrams from the microcrystalline information. We typically publish median values in our roadmap, and so all the diagrams show this and not average values. And the contribution you can see in the right lower corner, we have about 45% of material and equipment suppliers. We have nearly 30% on cell and module manufacturers, but also R&D institutes and others. Now coming to the PV learning curve. You see that, say, last year, even we have had COVID-19, the, say, installed capacity was slightly increased compared to 2019. So last year we have at about 135 gigawatt peak installed, and the average price was about $21 per watt peak. So that means that we have a complete installation worldwide end of last year of about 760 gigawatt. And most of the production capacity end of last year was crystalline silicon based. The learning rate continues since 1976 and with a similar factor, but if we count only the last years, so from 2006 on, say the learning rate is increased to about 40%. And so this is also a reason because there is a significant change in module sizes and concepts in the last time, and I will show some diagrams later on. And we see that this also gets premium prices with new formats, but the PERC is still the working horse in the technology. So how we calculate this average price? In former times, we have mostly used the microcrystalline data, but as you see in the left diagram, in the last 6 years, the microcrystalline part was decreased drastically and the monotype materials gained the most of the market share. So we decided this year to make a kind of average calculations for this module price, or say price per watt peak. So we take into account the ratio from mono to microcrystalline, also to the amount of new formats, because as I said, they have got higher prices, and also to the bifacial modules, which get the highest price in the products. So taking all this into account, we came up to this $21 per watt peak. Now coming to the materials, starting with the wafer. And we just heard it in the presentation before that, say, the wafer thickness is one of an important factor, because the silicon is a reasonable price in the material cost for the production. This year, we have at about 12 grams, or say for M6, we have 13 grams per wafer, and this will decrease to about 10 grams. But we offered and we asked for the different wafer sizes. So how many silicon I really have to use to get the bigger wafers. Of course, larger wafers needs more polysilicon. This is clear. But if we count per watt on the wafer, we see that the bigger wafers need more silicon. So this is a little bit surprising, but we will, observe and watch this in the future. That's maybe one reason, because the technologies are not as mature as, say, the smaller wafer sizes. Also, the silicon wafer thickness is decreased, as we heard before. And for the P-type mono, this is at the moment something, as we just heard, between 170 and maybe slightly less for the smaller ones, and will drop down to about 150 in 10 years. The N-type materials is already thinner. So there we have already, say in 10 years, less than 140 micrometer. And the heterojunction is even thinner in the wafers, because this time we only ask for the size, not for the technology. This is the reason why the median value is not focused on the very thin heterojunction. Now, let's look for the different kind of materials. As I said, the last 6 years, we saw already that the mono was increased. So the complete mono share will further increase, but now, say, the N-type material will become a bigger portion in the increasing area. And the P material is still used for the P-type PERC technology, and this change in the doping materials, so from boron to gallium, this is now, shifting the quality and gets also less LID problems. And now coming to the influence on the wafer sizes on the drop, we made here, say, an insert in our learning curve for the different kind of wafer sizes. And here you can clearly see in the last 3 years, so say from 2018 to last year, we have had a drastic increase in different kind of wafer sizes, up to the G or M12, what we heard just in before. And we see clearly that the M2, so the original long time wafer size, is disappearing. And at the moment, M6, 10, and 12 are dominating. And this is clearly shown in this diagrams where we distinguish between the mono material and the crystalline or the casted materials. And here you can see that, say, the G1 and the M4, the smaller formats, will really disappear. And at the moment, the biggest share is the M6. But in the next years, between M10 and M12, the share will be more or less half-half in the future. And similar, it will be also for the casted materials. So for the smaller M6, this could stay a little bit longer because this is possible with upgrading the older M2 cell tools. But if one would like to go to M10 or M12, we need really new tools and new fabs for this size. So how the crystalline, the cells will develop in the future, and which kind of technology. As I said, the PERCs, including TOPCon, are still the working horse. So it's about more than 80% in the market, and this will more or less continue. This old aluminum back surface field will, yes, disappear in a few years, so latestly 2025. And the silicon heterojunction will increase to about 15% in the next 10 years. And also the back contacted concepts, and also tandem will appear. So tandem we see may come on the market around 2023 onwards. And all these green marked areas from TOPCon, PERCs, and silicon heterojunction, these are technologies which are bifacial ready already. So how to, yes, decrease the price on the products? One big part is, of course, the silver price. And we see here that for the M6 format, we have at the moment something about 80 milligrams silver necessary per cell, and this will decrease to 50 micrograms. But the N-type concepts, like the TOPCon as well as the heterojunction, need much more silver. So the reduction needs to be done, and will of course be done with the reducing of the finger width and more bus bars. As you can see, the finger width will decrease down to 20 microns. And also the print process will help to reduce the silver amount in the future. And we see a clear focus also to, say, more bus bars, as we have seen also before. Say the main is now between 9 to 12 bus bars, but also more than 12 bus bars or bus bar less will come in the future, which also will help reducing the silver amount and the costs on the cells. Now, which kind of efficiency the different technology may reach in the next years? We see here that, say, the microcrystalline product, of course, is the lowest one, which is, say, at the moment around 21, a little bit more than 21% on the cell basis. But if we go to the mono, we see that also the P-type material reaches at the moment 23%, and the N-type materials like the PERCs or heterojunction are in the range of, yes, 23.8 to 24%. And in 10 years, say the N-type PERCs with the passivated contacts like TOPCon would be very close also to the silicon heterojunction with about 25.2%. And the only, say, possibility to overcome the limit on the single junction is the tandem, and we see here that the tandem will be expected in 10 years with about 28%. We see here, and this I think could also be seen in the presentation before, say the new fabs for cells are mostly around and bigger than 5 gigawatt per fab in the future. Now I'm coming to the modules, starting with the interconnection materials and the interconnection technologies. We see here that the lead-containing soldering is still the dominant technology, but lead-free as well as conductive adhesives will gain market share in the next years. And the materials are, of course, mostly of copper, and the ribbon will, say, be overcome from the copper wire, because this have some advantages on the light gathering in the cells. The other big part of costs in the module is the glass, of course. Last time BNF showed that about 30% of the non-silicon materials costs in the modules are coming out of the glass. At the moment, the glass is on the front side still bigger than 3 millimeters, but say the smaller ones, so between 2 and 3 millimeter, will come up. In the back side, it's mostly already the thinner one between 2 and 3 millimeters. But say bifacial materials are mostly glass, and this is parts which will come up in the future, as you can see at the lower right part. But the glass foil is at the moment still 80% on the market share. So how to gather efficiency or more power from the modules? And this is what we have seen. Say they cutting the wafers in half, or at least maybe sometimes a third. So the cell to module power ratio can gain by cutting from a full cell to a half about 2% out of the power. And this then results, of course, in, say, module efficiency. And we think that this is the best to differentiate between the different kind of module types, not the absolute value of watt per module. And if we see here and compare for the N-type material, we see that the modules in 10 years, there is nearly no difference between the TOPCon types and the silicon heterojunction. We will end up there with about 33%. But with tandem, we may reach 26%. Now, how many is cutting half, and how many cells are still used in full? And you see here, this year it's only about 10% full cells and nearly 90% half cells. Only the bigger wafers than M10, they may be cut mostly in third cells. And say the form factor, so how many half cells a module have, we see here clearly that, say, the bigger parts, or the 144 half cell module types are, say, about 2/3 or 60% of the market. And the other, 40 or 35% is the smaller ones. And this is, fits to the market between rooftop applications and also, say, power plant applications. Now coming to the size of the modules, and here are also the two, say, applications important. One is, of course, for the residential or for the rooftop, and here, say, size is also increasing, but here the weight also has to be considered. So the sizes are, say, in the range between 1.7 to slightly more than 1.8 square meter, with the biggest part at the moment in between somewhere, depending on the cell size. And this then results in module weights from, say, at the moment, not mostly smaller than 20 kilograms, but we see that in the future, they will even grow to more than 22 kilograms. But for the power plant applications, of course, weight and size is not the important factor. There you will have more power out of the module, so having less costs from the other BOM materials. And here the sizes of the modules will even increase to more than 3 square meters in the future. At the moment, it's still between 2 and 2.5 square meters, but as you see, that will increase. And this also results then in a more weight per module. And of course, for this, you have to find a good possibility to get the materials automatically and yes, cost efficiently mounted in the field. Most of the modules are still monofacial modules, even if we have bifacial cells in the modules, as here shown by this orange parts. But this year we have already about, yes, 28% on bifacial modules in the market. And as I said, the heterojunction and TOPCon concepts are bifacial ready, other PERCs as well, but this TOPCon heterojunction have the highest bifaciality factor. So it means you get the highest power out of this bifacial modules. Now, what does it mean for the product development in the future and for the product warranty? As I said, there is a change in the doping, is going to gallium. And this is one of the reasons why this first year degradation will drop from at the moment about slightly more than 2% to less than 1% in 10 years. And so also the performance warranty would increase from the 25 years over to the 30 years in 2031. And the product warranty also will go up to 15 years. And as I said, it's by the doping material is one reason. Then also, say, the introduction of multi-bus bars or bus barless, and also by, say, improving the optical inspection technologies and the control. And also in the module, there is a lot of improvement with the half cells, with the PID resistant encapsulation materials. Then the electroluminescence inspection is already standard at the moment, and also MES is implemented in a lot of fabs already. This also help to say get better conditions and get a higher and better warranty for the customers. And as I said, the smart fab is yes, increased. We see that the MES and machine learning will be implemented in the fabs. The electroluminescent is about 100%. So in every new tool, the automatic optical inspection and MES will roll out. So it's a moment from say 50 to 60% will increase to more than 90%. But others inspection also will coming up. And also the trend of the automation will increase, which helps to get the better product and higher quality out of the systems. So the fab logistic automation is increasing and going in the next years to more than 80%. Then MES is standard already in tools, more or less. And the automated log track, LOT tracking will also say be implemented in the most of the fabs in the near futures. So this all will help to get higher quality products. So I'll have a short look to the future of the PV. We typically have, say, different scenarios, what we are looking for. One is the BNF NEO, where we have in 2050 about 22% global electricity, but also two other scenarios from Professor Breyer with, yes, 69% global electricity outlook, and also 69% global energy outlook. And in all three cases, you see that the actual shipments were, yes, higher than all the projections in the calculations. But you see, there is a big market in every case. So even in the smallest one with, say, market peak of more than 400 gigawatts per year. But this is the lowest part, yes, assumption. So we have had several 100 gigawatt market in the near future for the photovoltaics. And we will help all the developers on the PV to get the requirements for this future needed market. And so we will provide the future guidance to handle the PV. Thank you very much, especially to our contributors. And you can find the complete roadmap on itrpv.vdma.org. Thank you very much.
Jutta, thanks a lot. I think that was exactly on time. Perfect. So nevertheless, let me ask one question. I think the great thing is we also have Marcus here, who was also instrumental, and I see him on the chat actually for ITRPV. So that means if you have questions, please feel free to ask them in the chat, and that should be answered. But maybe one from my side, Jutta. So if you look at the ITRPV roadmap today, the new one, which you just released, and you look at the one from last year, so where are the biggest changes that have happened compared to last year? So when you look at the forecasts, because as you showed also in your last slide, the forecasts always vary in solar, and in the end, it's usually getting better, even if there are some slight bumps, but in general, it's getting better, it's getting more. And so where are the biggest changes you are seeing when comparing your newest analysis to last year's?
I think one, to me, important factor was this degradation for the first year, or the drop in the first year degradation for the future. And I think if I have showed that the doping on the material is changed, and it was really drastically changed from the last year to this year. So for the new production sites. So if we have more of this, so we will have a higher quality, higher efficiency, so faster in this, we get less problems with LID. So this was one of say, to me, astonishing factor that you really can have a shift even in the technology if you change one parameter more or less drastically.
Okay, okay, thanks a lot, Jutta.